The classification of two manifolds is one of the most classical topics in mathematics. It's maybe 150 years old. The first rigorous proof by Klein and Diecks is from 1907. We can also look at it algebraically. There's a connected sum construction. If you have two manifolds, we can dig a hole in one and dig a hole in the other and then connect them. So this is called the connected sum. Obviously, if you connect a sphere, then nothing happens topologically, so we can define this as a homeomorphism, right? If you add a sphere, you don't change anything, and we have equivalence classes of manifolds. Now there come in two different classes, so there is the orientable case and there is the non-orientable case. So the orientable case is always a sum of tori. Two tori, and the non-orientable case is a sum of projective planes. So that's the story, and the proof is not that difficult. It can be also done in the discrete. What you do is you just start building up your manifold. The manifold is locally Euclidean, so in the discrete it's just a wheel graph locally, and then you build up your graph until you have identifications on the boundary, and these identifications on the boundary come in two different types. Either you have this orientation, kind of in this case the orientation kind of here reverses, but that means you add a ribbon like this. This is a picture of Klein and Diecks. Or if it is like this, then you have a Möbius strip. And so there are two different type of identifications, and then you just have to understand what happens on the group level. The fundamental group plays an important role. That's also what Klein worked on, and also Van Dijk, one of the first group theorists, he coined the notion of group. Van Dijk, he showed that if you take a Klein bottle, I just got a new one, I had bought it about 3 times, they usually break, especially if you show them around a lot. So this is a Klein bottle. This is a two-manifold, a non-orientable two-manifold. If you add to a Klein bottle a projective plane, kind of your Kreuzkappe, you add a Kreuzhaube, Kreuz, that's what Klein and Diecks called it, and if you do that, it's the same then when you do it to a torus. So there is kind of, obviously there is no way to build a group which contains all the manifolds, right? So this is the first question I was looking at this week. This week I had some fun with this group completion question. Can you complete these monoids in a natural way? Of course, every monoid can be completed, and so in this case these monoids are not that interesting. They are just the natural numbers, right? Because they are generated by one element, and also here this is also just a natural number, so the group completion, you can say, are the integers. But that's not the ultimate story, and the reason is because we have an asymmetry between these two worlds, right? What happens is maybe best seen when you look at the Euler characteristic. The Euler characteristic in this case is 2 minus 2k, and here 2 minus k. So the torus counts somehow like 2. And it's obvious when you look at it from the Morse perspective, which came after Klein and Diecks, but Klein and Diecks already kind of saw you have to first build one connection, that's kind of adding one cell, right, in the Morse decomposition, and then you add another cell that produces you then addition of a torus. Some sense the torus is compound. It's made of two particles, and I like to kind of think about geometric objects also as particles. We cannot complete the union, but we can complete each of these monoids naturally, and both of them just naturally become the dihedral group, infinite dihedral group, which is my favorite group because it's a natural group. I wrote about this in 2022. The integers are not natural. It's an abelian group, but it's not natural. It doesn't come from the topology alone, but the infinite dihedral group is natural. You can get it from the topology. So also, yeah, we want to fix this asymmetry, and in order to fix this asymmetry, we just break up the we break up the torus. We break up the torus, we make kind of half tori. And that's kind of already in that picture of Dehn and Heggard from 1907. On the level of the fundamental group, they have different structures, and these dihedral groups, they are just generated by two generators where both are kind of like this Pauli principle, both of them, you know, you cannot do twice P, not do but twice Q. So we get just words like A, A, B, A, B, A, A, B, A, B. So these are the positive orientable cases and the negative orientable cases also here. So the integer genus, the number of letters you have in a word, for the positive case, that's kind of a positive genus. In this case we have negative genus because we start with B of P here or Q. So P is the projective plane, Q is the anti-projective plane, and so you generate the group with these generators. And things become now more symmetric, and you have a picture which looks still different. I mean, the picture doesn't change here, but we have kind of just more structure in these manifolds if we extend them and if we form a group. I tried also to build a group, of course, which contains all the manifold, but that doesn't work because of Van Dijk's theorem. It's one of the most remarkable results, and there are many animations you find on YouTube. Maybe I show one here, a beautiful one from about 10 years ago, which shows that if you add a projective plane to a torus, then you get the same thing if you add the projective plane to a Klein bottle. So it's kind of clear from that picture of Dehn Heggard already, once you are able to go from one side of the manifold to the other, if there's only one side, if you add more of these possibilities, it doesn't matter, you still can go from one to the other. So but then you have to do some group theory transformations on the level of finite percentage groups to see that we have the same thing, or just give a deformation from one to the other like this animation shows. So that's what I wanted to say today.